These are kind of the big picture items. Redox stands for oxidation
Is
reduction
this for the test?
So this, yeah.
Oh wait, no, your left's right. Wait,
This
hold
is-
on.
Why is it
Hold on,
reduction
hold on.
oxidation?
We're not doing the thing yet.
Because it does
Yeah.
read
Oh, that's a good question. Huh. Oh,
I mean, that would make sense. That would help you remember it.
Oxide.
what was the other thing? Oh, the SI base
You could do
units.
like oxidation.
Remember how SI base units are actually the International System of Measurements? It's the same thing. But that's French, System International, or whatever you say in French. But so maybe it's derived from French.
I think we should call it oxidation.
Oxroid?
Oxidation.
Oxroid?
Reduction and
Yeah.
oxidation. You just said it.
Okay. So these are the big picture items. What is a redox reaction? That's the first one. That is going to require oxidation states. So kind of, I don't know, as a caveat here, we need to make sure or could practice with how do you find oxidation states. Remember, there are a few constant ones. So we've said aluminum is a positive 3, zinc is a positive 2, cadmium always a positive 2, silver always a positive 1. Column 1A and column 2A respectively are always their proximity to the noble gas. So we can derive some oxidation states from there. There are others. Those are not the only ones, but those are the most common ones. So those are the ones I would need you to remember in terms of the constants. Otherwise, you could have multiple oxidation states. So iron 2 ion, iron 3 ion. I have to give you enough information. So if I give you the name, the actual name, you could find the oxidation state. So for instance, if we said something like iron 3 chloride, you would know the oxidation state of iron is a positive 3 in that situation. And I don't know if I've ever said, it doesn't officially matter to me whether you write positive 3 or 3 plus. There is a difference in science, but it doesn't matter to me, so you write it either way. So that's one option. Or I could give you the chemical formula, and then you derive the oxidation state based on that. So for instance, if you have something like, let's say, sodium, let's say, ammonium, I'm sorry, thank you, ammonium phosphate, we could derive the oxidation state with multiple steps. It might be easier to take this ion and separate this ion and separate it out, but eventually we would derive something that says phosphorus is a positive 5 on there. That could be helpful. But most of the time, it's actually more helpful if the chemical formula is for something that has multiple oxidation states. So something like CuCl versus CuCl2, where the copper here is a positive 2 and the copper here is a positive 1. So that's generally speaking, I either have to give you the chemical formula, or I have to give you the name, or it's based on what oxidation states are constant. So those are the must situations. The other thing we'll add in here is any element by itself. And by element, I also mean Hofbrinkel, right? So the homonuclear diatomic molecule ones, not just any other type of element as well. So let's say iron by itself has the oxidation state of 0. So if this was solid iron, if you have H2 gas, that's also an oxidation state of 0 as well. Any monatomic anion or cation. Right. So if you had something like K plus, the oxidation state of potassium ion is a positive 1. Ca2 plus is a positive 2. S2 minus is a negative 2. Okay, nothing crazy there. The charge of the ion is the oxidation state of the actual ion.
Question.
Yeah.
So with the Hofbrinkel, you're saying H2 is equal to 0, but that's not true for O2?
It's not true for which one, sorry?
O2?
It is. Any of the Hofbrinkels have an oxidation state of 0, and then any element that's in its constituent form, so at room temperature and pressure, as written on the periodic table, if it's not Hofbrinkel, it still has an oxidation state of 0 as well.
What about like your copper chloride?
Mhm.
Like, so is it an ion?
Nope.
So it's balanced.
Yeah.
How would
So
it be balanced if like 2 chlorine is a 0?
on this one?
Yeah.
Yeah, this would just be a positive 2, and this would be a 1, negative 1.
Well, you just said that they're equal to 0.
Yeah.
Are they equal to 0 if they have negative 1?
No, in here, yeah, good question. In an ionic compound, they can't be 0.
Oh.
So if it's only by itself, by itself, sorry, yeah, by itself. By itself. If it ever shows up in a compound, whether it's molecular or ionic, polar or nonpolar, doesn't matter, the oxidation state will not be 0. Because some sort of electron density is being distributed permanently or partially towards one region or another. Yeah, good point. Okay, what else? And then polyatomics, the oxidation state of those are predetermined already, right? So phosphate, 3 positions away from the noble gas. Oxidation state of the entire compound is -3, or the entire ion, -3. Okay, nothing crazy there. Arguably, this is not super helpful for us. The rest are. Okay. All right, half reactions. Ask these 2 questions. What's oxidized? And what's reduced? So let's start there. Okay. Remember our kind of timeline here, not timeline, but numerical line. If you have any values of charges, when we're going from a negative charge towards 0, are you adding electrons or removing electrons? So if you have something that is -10 charged overall, and you go to 0, electrically neutral, adding or removing electrons. Negative becoming less negative. You're adding electrons. And if you add electrons, is that still true? Or I'm sorry, removing electrons. If you remove, all right, in my brain it made sense. If you're removing electrons because your charge is getting less and less negative, more and more positive, is that still true as you go from 0 to 10? Yes, you're still removing electrons. When you remove electrons, that's the process of oxidation. So oxidation is the loss of electrons. We might say it like this if you check back in your notes. Oil rig is kind of the acronym there. Oxidation is the loss of electrons. Reduction is the gain of electrons. So anything that's reduced is gaining electrons. Anything that's oxidized is losing electrons. So reduction occurs when you're reducing something when you ultimately add electrons to make something less positive, or to make it continuously more negative. Okay, and this can go out to infinity, but the charges typically don't go beyond 10 for us either way. All right, so let's do an example of that. What if we have, let's say, F2 gas, homonuclear diatomic fluorine going to 2F minus. Is that an oxidation or a reduction? F2 to 2F minus. Forget the 2, just the oxidation state of fluorine, homonuclear, is 0. Oxidation state of the monoatomic ion is a -1. Right? Those are our rules here. Any element by itself, including Hofbrinkel, monatomic ions, and -1. So oxidation or reduction?
Reduction.
That is a reduction. So I'll just start diagramming it like this so we can kind of keep track of what's actually occurring. We go from a 0 to a -1. That is the process of a reduction. So what we would say there is fluorine is reduced. That's the language you would end up saying. Fluorine is reduced. The question of is fluorine acting as an agent to do something in a chemical reaction? The response would be yes. So we're going to throw in a couple other words here. The oxidizing agent is the species that's being reduced. Okay. So notice fluorine is being reduced, so therefore it is the agent that causes something else to be oxidized. That's how you would end up saying that. Fluorine is reduced, so it is the thing that's causing something else to be oxidized. So that in essence means something has to be giving fluorine electrons, fair? And because fluorine really, really, really wants those electrons, it's going to take it from it and force it to give up its electrons. So now we have a new word, which would be the reducing agent. Take a guess what the reducing agent is.
The one not being reduced?
Yeah, which would be oxidized, right? So this is being oxidized.
That's weird.
Yeah. So how do you remember these? Say the opposite, right? The reduced oxidizing agent is reduced, the reducing agent is oxidized. So whenever the word agent comes into play, say the opposite. So the reducing agent is oxidized, so it's giving up electrons. Therefore, it's the thing that causes something else to accept those electrons and to ultimately give them to something.
It's irrelevant, but you said oxidizing instead of oxidized.
Thanks. It works out in the brain somehow up there in the old.
And it was the right like word, just
Was
not
it?
the right
Oh,
form of it.
All right, so let's do that then. If you have sodium, and it goes to the sodium ion, what is the nature of the sodium? Was it oxidized or reduced? It's oxidized. Oxidation state of any element by itself is 0. Oxidation state of a monatomic ion is the charge of the ion. Again, I'll just kind of draw these lines to keep track of what's actually going on here. So this is oxidized. If something is oxidized, something will be reduced. It is very unlikely that in chemistry we have free electrons doing nothing. In physics, we would harness that energy somehow, move it through a system, create a potential difference, and then apply a current, or current would be applied, and now you have electrical work being done on the system. So we in chemistry will harness those electrons via an actual chemical reaction. So the cool part about this is now we can combine these two things together. So if we, let me step back, this is the half reaction. That term shows up on the board on the other side, so half reaction. This is the half reaction for what's being reduced. This is the half reaction for what's being oxidized. Very helpful to kind of separate it out that way.
So half reaction is just when something, it doesn't have both parts?
Yes, right. And in terms of balancing the half reaction, we have to have the equivalent numbers of atoms on both sides, right? So we do. So we have 1 and 1 and 1 and 2 and 2. But in addition to that, you have to show where the electrons have gone. So in this scenario, 2 electrons are needed because 1 electron reduces 1 fluorine, the other electron reduces the other fluorine atom, right? So you need 2 electrons for 2 fluorines to produce 2 negative charges. What would we put here? Where would the electron be? On the reactants or on the products? Keep going. There you go. There you go. Would be 1 electron here, like this. So sodium atom loses 1 electron, therefore it's pushed it off and it has to be going somewhere else. So now if we try to bring these reactions together, we can say something like fluorine gas reacts with the sodium metal to produce a fluoride ion and the sodium ion. Okay. Now let's balance it. Will these 2 ions experience an electrostatic force of attraction to help create a solid crystalline structure, aka do you form an ionic compound? Will these 2? Yep. Okay. So let's put those 2 together, it's fine. So this is NaF. Go ahead and balance the molecular equation like you have before. You need a 2 here, so that means you need a 2 here additionally. Nothing crazy. Base state here, solid, fine. Okay. And then oxidation state of any atom by itself. Any atom by itself, that's what we just proved here. And that's what we just proved here. So again, we're combining the 2 half reactions together. We could go ahead and just put in all the numbers, but I'm trying to do it step by step. What's the oxidation state of sodium in this compound? Plus 1 and fluorine? Minus 1. That's consistent with what we showed up here as well. And now we need to balance the electrons. So how many electrons were transferred in this reaction?
1 per
1 per,
product.
what did you say?
Product.
Per mole of product, okay. So this sodium, we say again, and I'll keep drawing these arrows just because I think it keeps track. You don't have to if you don't want to. The sodium is oxidized. It loses 1 electron per mole of sodium. So maybe we could say that like this, per mole of sodium. There are 2 moles of sodium. So it looks like there's 2 electrons that are moved. And same thing here, right? This fluoride or fluorine goes from 0 to -1, so that's a reduction. It required 1 electron per mole of fluorine atom. So if you have 2 fluorines, you need 2 electrons, and we got those 2 electrons from sodium, right? So sodium gave up the electrons. Is it the oxidizing or reducing agent, sodium?
Reducing agent.
Okay. So it is the thing that causes something else to be reduced, right? So we would say sodium is the reducing agent, and we would say fluorine is the oxidizing agent. It's the thing that caused something else to have to give up electrons. Okay, so a lot of steps in terms of keeping track of the details, but we definitely went way overboard with trying to draw things out. You could arguably do this in a much simpler way and just balance the equation. What's oxidized, what's reduced, 2 moles, 2 electrons, you're done. You could leave it at that. You don't have to go through necessarily all of these individual steps over and over and over again. All right, let's try to figure out the oxidizing strength of the halogens and see if this makes sense. All right, try this. So let's put F2 gas, sodium chloride solid. Let's do F2, sodium bromide. Same thing. We'll just do a few here.
Did you already talk about the total electrons transferred?
That,
Is
you,
that what we
yeah,
just did?
that could be what this is. Yep, or it is what this is. If 1 electron per mole, the total number of electrons moved from sodium given to fluoride is 2.
And the balance in acidic and
Yeah, we haven't
basic.
done that. Yeah, we're building up to that. Yeah. Good. Okay, what about here? What type of reaction is this? Redox, of course. How do you know it's redox immediately?
Because you told us.
Oh, yeah.
Because
Well-
they're neutral.
What if we formed, let me write out the entire thing, that way, I guess, to be a little fair. How do you know that's redox without doing any of this other stuff?
That's chlorine changes.
What do you mean by that?
Like, it's by itself now.
Perfect, that's it, that's what you're looking for. An atom or element by itself that shows up in a compound on the other side, an atom or element by itself that shows up in a compound on the other side has to be redox, because in here, fluorine will never be 0. Sodium can never be 0. Same thing, sodium and chlorine cannot be 0. So therefore, if you're 0 on one side and you're not 0 on the other side, if the question just wants to know whether it's redox or not, you got it, it's set. I've seen one time on a final assessment where they had legitimately like 10 different reactants, complicated, chemical formulas are crazy, and then another 5 or 6 products. You would go through about 15 minutes of work to calculate the individual oxidation states of each one, but the question just wanted to know if it was redox or not. So one of the reactants was xenon, and on the other side, xenon showed up in a compound. So within the matter of 2 seconds, legitimately, you could be like, oh, that's a redox reaction, and go ahead and bubble in your answer that way. So it's a very quick method to just distinguish whether something is redox. You don't necessarily have to go through all the steps to do that.
So are single replacements always redox?
Then the question is, could they be classified as other reactions? Absolutely. Which one wins out? That's more of a like a discussion of theory than it is, let's just classify the possibility of being a single replacement or a redox reaction. So we could even have acid-base, that double displacement, that also could form a redox. We could have multiple different types of reactions all being simultaneously behaving in certain elements the same way. Okay, will fluorine go to fluoride? Yes, this is -1, this is a 0. So notice that chloride goes to chlorine. Which one's oxidized, which one's reduced?
Fluorine's being reduced.
And it's being oxidized.
Oxidized. We're going from -1 to 0. This is being reduced from 0 to -1. Will that actually occur? I'm not giving you any indication. Will that reaction actually occur? Forget redox. Do what Mia just did.
Yes,
Why?
because it has a greater lift.
There you go. Perfect. Fluorine wants this electron more than what chloride wants. Currently, chloride has it. That's why it's a -1 charge. Fluorine wants it more than it. It's going to take it and make chlorine give it up. Fair? And that's entirely based on electronegativities. So I think in here somehow the periodic trend of electronegativity definitely is absolutely essential for kind of a big picture overview of why things are doing the things they do. What about here? Will this reaction occur? Or this one? Yep, same thing. So this would be Br2 NaF plus I2, right? In all cases, is fluorine reduced? Yep. What about this one, where you have Cl2, let's do the reverse reaction, interacting with sodium fluoride to produce the sodium chloride and the fluorine gas. Will that occur? No, because
It's not an electron either.
fluoride has the electron. Chlorine is not going to take it to become negatively charged, forcing fluorine to give it up. Fair? So go ahead and create a trend out of the halogens, just the halogens. Give me a trend for what will take what and what will not take, what will take the electrons and what will not take the electrons. Keep going though. I mean, like, develop the actual trend
I just didn't follow once the electrons won.
from,
The ones below it.
there you go. So we could say fluorine will turn into fluoride in all situations, no exceptions, right? So this means if fluorine reacts with bromide or chloride, bromide, or anything that shows up below. So in terms of the periodic table, chlorine, bromine, iodine, so on. Right? In all situations, you will have fluoride being produced. Okay, what about chlorine? What will it take it from? Say it again though.
Everything below it. So chlorine will take from bromide and iodine.
So this means, oh, you know a better way to do this? Sorry.
Yeah.
Let's just plot it like this. Fluor, chloride, iodine.
Can't we just, they just take from below, right? Though, like,
Yeah.
that's it. It doesn't
Yeah,
change.
right.
So why are we doing
So
this?
I don't think we need a chart. I think
I
Doing
don't-
it.
I know,
Doing it.
I think this is worse than.
Doing it. Reaction or no reaction? Will fluorine take it
Oh
from
my
chloride?
god.
No.
No.
Nice. What about here?
No.
Here?
No.
No.
Mhm.
No.
Alright, so these are washed, these are no reactions. What about here?
Yes.
Fluorine wants it, chloride's gonna give it up. Fluorine wants it, bromine's gonna give it up. Bromide. What about here?
Yeah.
Here?
Yeah.
Chlorine's above bromide.
Mm.
Chlorine's above iodine. Sorry,
Yes.
right?
And then the
And
charge
this
is
is
mirrored.
all,
It's
these
just
are all no
mirrored.
reactions over here. Okay, okay, something like that.
Wait,
Cause chlorine won't take from fluorine.
Yeah.
Yeah, you're looking
Bromine
from the row to the
will
pole.
take it from
for some reason
chloride.
I was thinking fluoride would take from chlorine and then
Yeah.
you just put
Yeah,
reaction.
Good.
Yeah, no, I get it.
Okay, let's practice. Let's practice. We got it. We can do it.
You are so nice to your other classes and your